Welcome! Today we're going to explore the concepts of setting overrides, Kalman filtering and PWM and how they apply to the Alpaca version 2 driver. Now this video is advanced and it is entirely optional. It's really only intended for people who want to understand the internals of the driver or for people who are interested in optimizing its performance by adjusting key settings. So the best place to start before we start tweaking some of the knobs inside the driver is to understand how the settings are saved so that you are easily able to recover back to a known state, just in case anything goes wrong, which I'm sure it won't. So what I'm going to do is I'm going to first of all fix my site location. Just by clicking the locate button, it'll do its best guess of where we are located. And I've picked a site here in Brisbane, and I want to show what actually happens when you hit the save and restore button. And to do that, I'm going to call up another window. So what I've got on the right here is just the directory tree of the Alpaca Benro Polaris driver, which I've got installed on my mini PC. And there's a new directory called the data directory, which is where the settings are actually saved. So I've changed the location, and when I hit save, it creates a new file called config.pilot.json, and this file has got a list of all the properties that have been overridden by the pilot application. And what happens when the driver starts is it will read all of the properties from config.toml as defaults, and then it will read config.pilot.json, which are the setting overrides. So any setting that you change with this page, the Alpaca driver settings page, or any of the tuning settings that are available within the tuning pages, and there's quite a few, if you make a change, in fact I'll change this one here, if you make a change and then hit save, it will add that setting to your config.pilot.json so that next time you start the driver it will use that setting. Now if you've made a change and you want to get rid of it because it's not having a good effect, you can click the restore, and what restore does is it'll just delete this file and it'll go back to using just what's in config.toml. So since I did that, I've got to go and reset my location and resave, so we're back to a known setting. So I just thought I'd mention that about this file here. If you ever want to know what has been changed, you can just have a look in here and you can see the properties that have been changed. Okay, so that wraps up the setting overrides. That's all I wanted to mention on that. So Kalman filtering and PWM. So these two concepts were to solve two key problems that we had to overcome with the Polaris. One was we needed to improve the accuracy of the mount, and the second one was how the heck are we going to control the speed when all we can do is go slow 1, 2, 3, 4 or 5. If we really want to track sidereal motion or lunar motion, we need to have much finer granularity of control of speed, and we need better accuracy. Now in terms of accuracy, I'm also going to turn off Kalman filtering. And what you'll notice when I zoom into each of these dials is there's a lot of jitter from the sensor readings of the Polaris. It's sending back a telemetry of saying, oh, my current azimuth is 181, 7 minutes and 22, 24, 23, I'm not sure what it is, but it's jittering around in the arc seconds. If we want to get a really accurate mount, we need to filter this or smooth it out a bit. And I'm going to come back and return it back on again. There is a Kalman filtering page which gives you a better view of how much jitter there is actually in the signal that we're getting back from the Polaris. And if you look at this blue line on the left, this is a chart of the angular position of motor 1, which is around 181 degrees, and you can see it's jumping all over the place. I think we get a new sample every 200 milliseconds. And the white line is how the Kalman filter has sort of smoothed it out a bit. It's still going around a bit, but it's smoothed it out quite a bit. If you look at these figures down the bottom of the chart, it's basically saying that if you take an average of the blue line, motor X, motor 1 in this case, the typical standard deviation away from that average is 0.34 arc seconds. And then if you do it the same sort of thing for the white line here, is 0.14. So we've sort of halved the variation of the position, angular position signal for this motor. And for motor 2, we've done a bit more than half, and for motor 3, it's probably a bit less. You see motor 3, it doesn't update the signal as often. But anyway, so that's what the Kalman filter does. It makes the sensor readings a bit more accurate and consistent, which we need for the basis of knowing how to move them out. The right-hand chart is very similar, except this is based on velocity. So the blue line is the reading that we're inferring from the telemetry getting back from the mount, and the white line is what we have filtered it and smoothed it out to be, and the green line is what we're asking the motor speed to be running at. So there's a couple of test buttons here. I can just click this one and you can see the set point has jumped up to 0.18 degrees per second velocity, and you can see the positions slowly increasing up to 181, 0.36, 0.38 and so on. And you can see how we've filtered the blue jiggly line, and we've got a much smoother estimate of what the velocity and the position is. So this is going to help our accuracy. Now you can tune the parameters of the Kalman filter model, and I actually think the default's probably fine. You probably don't really need to tune these, but just to give you an example of one setting that we could tune is once we zoom in and get a bit more visibility here. This position here, the angular position measurement error, I'm just going to explain just this one. This is our estimate of how much measurement error is in this blue line. If we think it's really accurate and we want to follow it exactly, we can turn this down to 0 and say there's no error in this blue line. I want our estimate of the position to follow exactly what it is. It's gospel. And you can see now we've got a very shaky white line. As we increase our uncertainty or the measurement error that we think is in that angular position, it actually smooths it out and takes a better, more average measurement of the position. Now the key, and then there's another setting here that you can change. The key thing you want to do, just as a guide, if you do change these, is there's a measurement called the Kalman gain, which is an indication of how much of the actual telemetry you're getting back are you going to use in the estimate of where we are. And you want to have, if you want to adjust these, if you push this right up to a very high number, you want to make sure that your Kalman gain is at least 0.15. So you want to bring up this number as well. And it'll settle down. There we go. That's a reasonable setting. So otherwise, you're going to be ignoring the measurements. You want to make sure the Kalman gain's at least 0.15 or higher. I usually try and have it about 0.16. But as I say, I think you can leave these pretty much set as the default. In fact, I'm going to go do a restore, set my location again, just so we get back to what we were. So that's what Kalman filtering is. It's pretty simple. It's really just trying to smooth the telemetry from the Polaris so that we've got an accurate basis of working out how to drive the motors. Now the key problem in driving the motors that we have is Polaris only gave us 5 commands to move each motor at a slow pace. The slowest pace that it can go is 0.006 degrees per second, which sounds pretty slow, but it's not slow enough if you want to do sidereal tracking, which is a rate of 0.0042. So it's even less than the slowest of the slow rates. So the way we overcome that is using what's called pulse width modulation, PWM, which provides a way for us to get intermediate speeds between the different slow rates. So the test movement that I've got here is showing that the slowest rate is 0.006. I'm spending 50% of the time down here and 50% of the time at rate number 2. And if I do that, half on each, you can see that the blue line averages halfway in between. And I actually can change these. If I say I only want to spend, let's say, 25% of my time, well, that's 24%, at the higher rate. So there's little pulses going at the faster rate. It spends more time at the slower rate. You can imagine that that's going to be a quarter of the way between the speed 1 and speed 2. So this is how we overcome, and we can now control the speed very finely between the different fine movement commands that we've got available from the Polaris firmware. This was key. So the settings here don't really affect the driver. They were really used by me to help discover what sort of cycle time we should be using, which is, I think we use about a half a second. Every half second we're sort of sending a command. In fact, I'll show you that. If I call up the driver log here, I can turn this on to log Polaris protocol. Here we go. If we do an actual control, this is what's happening behind the scenes. It's actually sending this many commands to control the speed of the motor. It's pretty amazing how much it's doing, but it's hard to read because it's going past so quickly here. But you can see it's traveling between speed number 1 and 2 and speed number 1 and 0 when it's eventually stopped. So there we go. So 2 key concepts. One was Kalman filtering to smooth the telemetry and get accurate measurements of our understanding of where the mount is pointing. And the second one is PWM. Without it, we wouldn't be able to control the mount at all. It gives us fine-grained speed control of each of the axis motors. Now, the next video we'll talk about how do we work out how large a pulse width to control each of the motors for to get the desired speed that we want. And that topic is all about the calibration of our speed controller. But that's for next time. That's all I've got for this video, and I hope you'll stay tuned for the next one. Cheerio for now. Bye.